Nuclear astrophysics is the study of the microscopic interactions within stars and the synthesis of the chemical elements in the universe. The energetic Big Bang created the first light elements, mostly hydrogen and helium, as it expanded and cooled. As stars and galaxies formed, nuclear reactions began to synthesize heavier elements, and this is continuing in galaxies like our own. This material is spread throughout the galaxy by explosions of dying stars. Without stars, there would never be carbon, oxygen, and nitrogen for life. Here we see the core of a star about 25 times heavier than our Sun. At the end of the star's life, which is measured in millions of years, rather than the 10 billion years our Sun will live, it has an onion skin-like structure with a heavy iron core and lighter elements near the surface. Pressure can no longer hold this up, and a collapse ensues because further reactions on iron use up energy rather than produce energy. At this point, the star detonates because the rest of the infalling matter bounces right off the core. This is called a core collapse supernova. In the extreme conditions of this explosion, many heavy elements are synthesized by nuclear fusion. One such nucleus, nickel-56, can decay via the emission of a positron and a neutrino with a lifetime of 6 days to cobalt-56 with the emission of gamma-ray photons. This beta decay, as it is called, not only helps form the iron core in the first place, but is also involved in the core collapse and determines the bright explosion light curve that we can observe from Earth with satellites and telescopes. Thus, nuclear physics determines nearly all aspects of the explosion, including what we actually see. Many of the elements we hold precious, such as gold, silver, and platinum, were made in nuclear reactions inside these supernovae and spread throughout the universe by the explosions. In the environment of a supernova, the very heavy nuclei can be formed by the repetitive fusion of neutrons to lighter nuclei. This is possible due to the extremely high temperatures and large number of neutrons available. An extremely common event in the universe is a stellar binary system where two stars orbit each other. In some cases, the smaller star can suck material, mostly hydrogen, off the larger star. This material then falls onto the surface of the smaller star, which can be a white dwarf or a neutron star. The material gets compressed so much that eventually it explodes in a thermonuclear runaway. During this very hot hydrogen-rich explosion, nuclei from the white dwarf or neutron star surface can fuse with protons, again building up heavier elements and emitting gamma rays. One such interesting nucleus that is made in these scenarios is aluminum-26. It decays with a very long lifetime, so that what we see when we look out into space is the footprint of 1,000,000 years of stars making aluminum-26. We can compare this map to our models of supernovae and binary systems to see if we got things right.